Rational functions. What is a rational function? Rational function is the quotient of two polynomials. Today, we're going to use and find the properties of rational functions to graph it. In order to graph a rational function, you must find its x-intercepts and y-intercepts. To find the x-intercepts, you set the numerator equals 0. For example, if you have the equation x squared minus 4 over x squared minus 2, you set x squared minus 4 equals 0, and you get x equals plus or minus 2. Therefore, the intercepts are at negative 2, 0, and 2, 0. For the y-intercepts, you set f(x) equals 0. In the same equation, x squared minus 4 over x squared minus 2, you get f of 0 equals 0 squared minus 4 divided by 0 squared minus 2. Therefore, f of 0 equals negative 4 divided by negative 2, and f of 0 equals 2. So the intercept is 0, 2. For rational functions symmetry, it can only have a y-axis symmetry or origin symmetry. We use the symmetry to help graph a rational function faster. For y-axis symmetry, if f of negative x equals f of x, then the graph has y-axis symmetry. For origin symmetry, if f of negative x equals negative f of x, then the graph has origin symmetry. For example, if the equation is f of x equals x squared minus 4 over x squared minus 2, you set an x equal to negative x, so you get negative x squared minus 4 over negative x squared minus 2. And f of negative x equals x squared minus 4 over x squared minus 2. Therefore, it is a y-axis symmetry because both f of x and f of negative x are both the same. For origin symmetry, f of x equals x cubed minus x over x squared. Negative x cubed minus negative x over negative x squared is f of negative x. And this simplifies to negative x cubed plus x over x squared, and this is the opposite of the original function, so therefore this is origin symmetry. For vertical asymptotes, they can only exist at the zeros of the denominator. So in x squared minus 4 over x squared minus 2, you set x squared minus 2 equals 0, and you get that x is equal to plus or minus root 2. So the vertical asymptotes are at x equals negative root 2 and x equals root 2. For n-behavior asymptotes, there's horizontal and slant asymptotes. If the highest degree of the numerator is less than the highest degree of the denominator, then the asymptote is at y equals 0. If the highest degree of both the numerator and the denominator are equal, then the asymptote is at y equals the leading coefficient of the numerator of x divided by the leading coefficient of the denominator of x. If the highest degree of the numerator is greater than the highest degree of the denominator, then the horizontal asymptote does not exist. Instead, there's a slant asymptote. If the highest degree of the numerator is exactly 1 greater than the highest degree of the denominator, then there's a slant asymptote at the quotient of the numerator divided by the denominator. For n-behavior asymptote examples, if you have the equation x squared minus 4 over x squared minus 2, the horizontal asymptote is at y equals 1 because the leading coefficient of the numerator and the denominator is 1 and both degrees are 2. So the asymptote is at y equals 1. For x minus 4 over x squared minus 2, you get an asymptote at y equals 0 because x has a degree of 1 and x squared has a degree of 2, so the asymptote is at y equals 0. For a slant asymptote, if for example you have x cubed minus x over x squared, you use long division to find that the asymptote at y equals x because when you that's the quotient of the division. For crossing points, they only occur with n-behavior asymptotes, so horizontal or slant asymptotes. For horizontal asymptotes, you set the function equals 0. So say you have the function x squared minus 4 over x squared minus 2. You see that you make x squared minus 4 over x squared minus 2 equal to 1, and you get that x squared minus 2 is not equal to x squared minus 4, so there's no crossing point. For the slant asymptote, you set the remainder of the division equal to 0, so you get say you have f of x equals x cubed over x squared minus 1, you get a remainder of x using long division, and you set x equals 0, and you plug 0 back into the equation to get a crossing point at 0, 0. Holes occur when a function can be simplified down as a result of one or more of similar polynomials in the numerator and denominator. Wholes cause a removal discontinuity. For example, say you have x squared minus x minus 2 over x squared plus 4x plus 3. You get that x plus 1 times x minus 2 over x plus 1 times x plus 3 when you simplify down, and you get x minus 2 over x plus 3. So you set the part you can factor out, which is x plus 1 equals 0, and you get x equals negative 1, and you plug that back in the remaining function, which is x minus 2 over x plus 3, and you get y equals negative 3 halves. So whole be at negative 1 comma negative 3 halves. Yeah, that's it.
Let's graph x squared minus 4 over x squared minus 2. The properties of this function has been shown throughout the video. The x-intercept is at positive and negative 2 and the y-intercept is at 2. The graph has vertical symmetry at x equals positive and negative root 2 and a horizontal symmetry at y equals 1 with no crossing points. There is also a y-axis symmetry to this function.